Today we're going to look at the squeeze theorem. Let's do a couple quick practice warm-up exercises here with some limits from yesterday. What's the limit as x approaches 2 of 3? 3, yeah, it's constant. It's always going to equal 3. How about the limit of x as x approaches negative 4? It's negative 4. Okay. How about the cube root of 2x squared minus 10, the limit as x approaches 3? Okay? Yeah. Remember, always try just plugging it in. If you know your parent functions, you know the cube function is continuous for all real numbers. Also, the quadratic is continuous for all real numbers. Alright, so if you plug in 3, you have 2 times 18 minus 10 is 8. Cube root of 8 is 3. 2. Too many 3s. Okay? How about this? The limit as x approaches 0 of tangent. 0 or does not exist? 0 or undefined? Okay? Got to remember how your tangent's oriented. Where are the asymptotes on tangent?
Tangent is y over x.
It's y over x.
So anything divided by 0.
Yeah, so when is x equal to 0, or the sign equal to 0? That's cosine.
No, it's at 0. Isn't the sign equal to 0? 0.
Sine of 0 is 0. When is cosine 0?
Oh, cosine.
Sorry, did I say sine?
Yeah,
Okay, sorry.
0
What?
is that 0, 1.
Yeah, so that's at pi over 2, right?
Yeah.
And at negative pi over 2. This is where knowing those parent functions is super helpful. Okay? So here's your tangent function, and we've got asymptotes here. So what is the limit as x approaches 0? It's 0. Okay? Now, if it were cotangent, it does not exist, because cotangent shifted over and the asymptote's right on the y-axis. Okay? Good review for us. Alright, the limit as x approaches pi of x times cosine x.
I got negative pi.
You got negative pi? Then you got the right thing. Good. Okay? Negative pi. These are both continuous for all real numbers, right? X is just a line. Cosine, its domain is all real numbers. So when you multiply them, it's still going to be all real numbers. So x is just approaching pi.
So we work in radians?
Yeah, actually in AP Calc, you're going to be in radians basically all the time. So, unless you're specifically told to use degrees for whatever reason, you'll always use radians. In fact, some of the trig rules are developed and they don't work if you plug in angles, like degree angles. They only work if you use radians. So, okay, so the limit theorem here, here's one that I've kind of alluded to in a couple of our examples, but I said, if it's continuous and you have another continuous one inside of it, then the whole thing will be continuous, so you can get the limit by just plugging it in. Well, here's a limit theorem that you can find the limit of a composite function by taking the limit of the interior function and then simply plugging it into the exterior function. Okay? So going back to C here, I could do the cube root of the limit as x approaches 3 of 2x squared minus 10. Okay? Well, we said with parabolas, since they're always continuous, we can just go ahead and plug it in. What is the limit as x approaches 3 of 2x squared minus 10? 8. So then I can take the cube root of 8 and I'll get my 2 again. Okay? So that's one property for composite functions. You can just take the limit of the interior function and then evaluate that into the outer function. Okay? Alright, so now we have the squeeze theorem. The squeeze theorem is kind of a interesting theorem, but it's used to find limits when we're dealing with a function that we are having a hard time working with. So let's read this here. It says if h of x is less than or equal to f of x, and those are less than or equal to g of x for all x's in an open interval containing c sub I, c, except possibly at c itself, and if the limit as x approaches c of h of x equals L, and the limit as x approaches c of g of x equals L, then the limit as x approaches c of f of x exists and is also equal to L. Okay? So, let's work our way through this. It's a lot of notation and stuff, but the picture is actually really helpful here. Okay? So, we have this function g of x. Alright? And we know that g of x is always greater than the other two functions, or possibly equal to them, but it will never be less than either of the other two functions. Okay? We also know that the limit is this value here, and let me go ahead and label that value L. Can you see that? Okay. All right. So then we have this other function h of x. H is down here, and we know that h is always going to be less than the other two functions, or possibly equal to, and we also know that its limit as we approach c is L. Well, the reason why this is called the squeeze theorem is because as we look at this f that we know now is between the two all the way, the limit, we have no other possibility. The limit has to get squeezed into that same value. It's kind of funneled in by these other two functions that are both approaching the value L from the top and the bottom, and it just kind of squeezes f right into that same value. Okay? Then after that, if they diverge, then f can move around a little bit more, but it's still going to be between them. Alright? But that's what's happening here. Okay? And all of those then will have a limit equal to L. Alright? Now, I feel like, why in the world do we need this? Well, there are a couple of specific trig limits that you're going to need to just memorize. Alright, so we'll star these here. Special trig limits that you're going to want to memorize. Both of these can be developed using using the squeeze theorem, okay? And we're going to actually illustrate that here, derive them down here below, okay? So the first one of these is that the limit as x approaches 0 of sine of x over x equals 1. And then also the limit as x approaches 0 of 1 minus cosine x all over x equals 0. Okay, so let's look at where this is coming from. So, we're going to actually go back to our unit circle. And we're going to use some triangles. Okay? We're going to use some triangles. Now, the area of a sector in the unit circle, you can see there is theta over 2. Okay, if we're in radians, the area of the sector, I'll call this S, is a ratio out of the entire area of the circle, which is pi r squared. That's going to equal the same ratio as the central angle over the full 2 pi of the circle. Okay? Well, if I were to multiply both sides by a pi r squared, okay, to solve for the area of a sector, S is going to equal, notice the pi's cancel out, and it's going to be theta r squared over 2. Well, if we're in the unit circle, what's r?
1.
1. Okay, so that's how we're getting the area of a sector here to be theta over 2. Okay? So that's the first step here. But what we're going to do is we're going to use areas. Since we have the area of a sector, we're also going to use 2 other triangles. One that we know will always be smaller than the sector. Okay? Because we're using a chord here. And the chord will always lie inside the circle, so it will always be a little bit smaller than whatever that sector is. Okay? And then we're going to use another triangle that goes straight up from this endpoint over here. Okay? And goes through that point where we have cosine theta, sine theta. And that's going to be 1 tangent of theta. Okay? Let's see, how do we know that that's tangent of theta? Well, opposite over adjacent is tangent. This is a right angle. Here's our theta. So tangent of theta has to equal opposite over 1. So tangent of theta has to equal tangent of theta. That means the y-coordinate has to be tangent of theta. Okay? Now, how do we get the area of the smaller triangle? Okay, what we're going to do there, we're going to go like this, okay, to get the height, alright? Well, the height of that triangle is the y-coordinate of that point, right? So that's sine of theta. So I know that the height is sine theta. and I know the base is 1, so now it's just 1/2 base times height, and I get the area over there to be sine theta over 2. 1/2 base times height. The base is 1, the height is sine theta, so it's sine theta all over 2. Does that make sense? Okay? So, I know that the area of this sector will always be between tangent of theta over 2 and sine of theta over 2. It's always going to be between those two. Alright? So that's the setup. Now let's actually derive the whole thing. So what we're going to do is we're going to multiply all three parts of this inequality by 2 over sine theta. Okay? So if I multiply this by 2 over sine theta, 2 over sine theta times sine theta over 2 equals 1. 2 over sine theta times theta over 2 is where I get the theta over sine theta. The 2's cancel out. If I multiply 2 over sine theta by tangent over 2, the 2's cancel, but then I have tangent over sine. And if you remember your trig identities, okay, remember tangent over sine. What does tangent equal? Sine over cosine.
There's 2 sines you cross out.
Yeah, times 1 over sine to divide by the sine. The sines cancel, so that's how we get the 1 over cosine. Alright? So, that's our first step. The next step here, one of the properties with inequalities is if you take the reciprocal of both sides, it will reverse the inequality. So that's what we've done here. We've made this cosine is less than or equal to sine theta over theta, which is less than or equal to 1. Okay? Now, here we're double checking in our proof to make sure that this would apply whether we have positive or negative angles. Okay? Since cosine of theta is the same thing as cosine negative theta, then this will still apply. Since if I do sine of negative theta, that equals a negative sine theta, right? Well, if I divide that by a negative theta, the negatives will cancel out and I'll still have sine theta over theta. Okay? So we're just confirming here, and you would have to do this if you were proving this. You have to confirm all possibilities. So negatives will work here. Okay? So now we want to actually take the limits. Okay? We wanted to figure out what the limit was as theta approached 0. Well, look at this bottom end, the cosine of theta. The limit as theta approaches 0 of cosine theta is 1. The limit as theta approaches 0 of 1 is 1. So, based on the squeeze theorem, the limit as x approaches 0 of sine of theta over theta, or sine x over x, is 1. Okay? Since those both squeezed it in to 1, we know that the sine x over x has to go to 1 as well.
But if we're using the unit circle, wouldn't there also be, as it's going to 0, it would be negative 1, 0, because we go around the circle?
Wait, I'm sorry. As x is approaching 0, or the theta is approaching 0.
Wouldn't it also approach 0 at, think, the point at the top, the point on the left, bottom, and the right as well?
No, don't think of it as the x coordinate. It's the angle.
Okay.
The angle theta is approaching 0. Yeah. Okay. So that's one that you've gotta know. All right. Now, we could do this as well in a similar way. Okay? We could do this in a similar way. Tangent of x over x equals 1. Okay? We could start with the same triangles. Okay, the same areas. Tangent of theta over 2 has to be greater than or equal to theta over 2, which is greater than or equal to sine of theta over 2. Okay? So, let's multiply. What do you guys think we ought to do here?
Multiply sine theta over 2 by 2 over 0.
Okay, that's going to get us back to what we did in the first proof.
2 over tangent is good.
Yeah, let's try multiplying by the other one. So let's multiply by 2 over tangent theta on all three parts. 2 over tangent theta times 2 over tangent theta. Okay, so the left side here is 1. And then the 2's cancel out, so we've got theta over tangent theta. And then here the 2's cancel out. You have sine over tangent. What's that going to come out to? Cosine.
Yeah.
Alright, cosine. So that's going to be cosine of theta. Alright? Now what do you think we should do? Yeah. This actually is the same as the previous proof. If I take the reciprocal of everything, 1 tangent of theta over theta, and now, or I'm sorry, this is, yeah, that's right. And then I'd have 1 over cosine, and I would reverse the inequalities. Okay? So what's the limit as I should do theta approaches 0 of 1? 1. What's the limit as theta approaches 0 of 1 over cosine theta? What's cosine of 0? 1. So we have 1 over 1, which is 1. Therefore, by the squeeze theorem, okay, since tangent theta over theta is always between those two, then the limit has to be equal if those are equal. So yeah, that's the limit as theta approaches 0 of tangent theta over theta equals 1. Okay? So that's another one. It's not one of the two really, really common ones that you should memorize, but it's just derived similarly to the sine one. Okay? So limit as x approaches 0, sine of x over x is 1. The limit as x approaches 0, 1 minus cosine x over x equals 0.
For this proof, do we have to show like that the negative angles work as well?
We didn't specifically, but we already knew it would work for the wait, what was it? The cosine.
Yeah.
Now the tangent is the same as the sine. Okay, tangent of negative theta equals a negative tangent theta. So tangent of negative theta over a negative theta will still just equal positive tangent theta over theta, because the negatives will cancel. So yeah, that would be a consideration. Thank you. Okay. Yes?
Do I have to state that consideration each time you do a question? Like negative thing.
Here it was just because it's a proof.
Uh-huh.
Okay? If you were asked to prove something, you should be careful about that kind of stuff with trig functions, but
I think when we do a question, if it was not approved, do we have to state that?
no. No. Okay. Now, we introduced the squeeze theorem, but the practice that you have here, if you look closely, it is a little bit more related to that, some review of what we've done, and then also a little bit more of that initial theorem with the composite functions. Okay? And then there is some element of the theorems that we just proved later on at some point. Okay?